Hello all, welcome back. We're going to now talk about the error in the alternating series. And there's only two errors that we need to worry about with the series unit. This one and the Lagrange series, and that deals with the Taylor-Maclaurin series. So I like this example because it actually shows you why the error is what it is. It's actually pretty straightforward. So the first thing it's asking us to do is to take this geometric series and write the first 6 terms of the expansion. And so this is actually very basic. What it's actually asking us to do is to say, okay, well, when n is equal to 1, figure out what the value of the series is going to be. And so we can see that this convergent series, right, it's going to converge. If I plug in 1 to my function, so I get negative 3 over 4, all raised to the second power, right? Because I'm going to raise it to the 1 plus 1 power. And so that first term is going to equal 9 over 16, right? Positive 9 over 16. And so in order to save some time here, I'm just going to go ahead and write out the next 5. And so my second term, when I plug in 2 right here, it's going to be negative 3/4 raised to the third power. So of course the series is going to be negative. So every time our exponent is an odd value, it's going to be a negative. And so my second term is going to be negative 27 over 64. And then I'm going to go ahead and raise everything to the 4th power, right? So n plus 1 is the 4th power. And so since it's an even, I'm going to get a positive number here. And that's going to give me 81, which we all know is 3 to the 4th. And that's going to be over 256. So right now I'm just basically listing out the numbers for us in our examples, just so we can kind of see the error once we get to it. So negative 243 all over 1024. And so when n is equal to 5, I'm raising everything to the 6th power, all right? And so this is going to be 729 over, by the way, this looks like a decimal, it's a negative answer. 729 over 4096. And then the last one I'm going to put over here for a reason. So our 6th term is going to be equal to 2187 all over 16384. Okay, so that's our first 6 terms. So now what it's asking us to do is find f of 5, the 5th partial sum. So what they really want us to do here to find the 5th partial sum is literally to take these numbers right here and we're going to add them up. So that's really what they want us to do. Okay? S right here, our S of 5. And to save some time with this, so S of 5 would be, so our decimal answer would be 0.39771. So this would be the summation of these first 3 terms. And so we want to now find the sum of the series, and we can easily do that, right? So the sum of the series is actually going to be equal to the first term, which we all know is 9 over 16. All right, so this is the equation that we learned for this. And it's going to be 1 minus what our r is. Well, our r in this case is going to be equal to negative 3/4. And so when we do that, we're going to get that this is going to equal to 9 over 28, right? 9 over 28. So that's the sum of our series. And if I wanted to actually find the decimal approximation for that, I get 0.32143. Okay, so right now we found the actual sum of the series, like this is the actual sum, and what the 5th partial sum is going to be. Okay, so what we're going to do now is we're going to find the difference of these 2 numbers. We're going to find the difference of these 2 numbers, and this is going to be the error of the 5th partial sum, right? This is going to be the error of the 5th partial sum. So with that being said, I'm going to take my difference, my S minus S of 5, and I'm going to do 0.39771, and I'm going to subtract, and this is the absolute value of this, I'm going to subtract what we just found there, 0.32143, and I'm going to get the value of this is 0.0763. So this is the error. This is the error, or the difference of our actual sum versus our approximation, our partial sum on the fifth term, right? So this is going to be the error that we have found with what's happening, all right? So that's the first thing. And the other thing I want to do really quickly is I want to just make sure that we bring this down here, right? So this is our sixth term, and find what the decimal equivalent of that's going to be. So that's going to be 0.1334839. Okay, so that's going to be our decimal equivalent to the sixth term. So what we can now look at here is, notice that the error you calculated is actually less than the absolute value of a sub 6. So this right here is going to be less than our s of 6 value. Okay, so what the value is, not the partial sum. And so what we can say about this, the n plus 1, and so our answer will never be negative, because it's the absolute value of whatever it is. But the whole point we want to make in this particular problem is that the following term, so what's the summary of this? So what we can always assume here is that the following term, all right, and so what I mean by that is that we were trying to find the error for s of 5, so we found the following term. We found s of 6, right? In this series, will be the maximum, the absolute maximum. So this would be the maximum error that can be. So what I'm basically saying here is that if I ask you find what is the maximum area for our eighth term, all you'd have to do is actually find the value of s of 9. And that's going to give you, again, the maximum error that this value, this partial sum, is going to be to the actual sum itself. So it's actually very, very, very easy to do. You just having to plug in the next highest value. Okay? So that's the idea behind the question. Now, it does get a little bit more complicated, so we're going to show you this example right here, right now. Okay, so what I already did really quickly was I rewrote our series from the top down here so we can kind of guess what would be the number of terms we would need, how many terms we would need to get our actual error to be correct to at least 20 decimal places. So the first thing that we would acknowledge here is I need to figure out what our n value would be. And so what we would do here is we would have to do the next term, right? So what would be the n plus 2? What would be the next term? Because we're starting at n plus 1. So this has just been n. This would be an n plus 1. So what is our value? So what n value would we have here to get this problem? So that's all we have to do is to solve for that. And so the first thing that we're going to do here is I'm going to go ahead and write 3/4 to the n plus 2. And again, that's less than 0.5 times 10 to the negative 20. I'm going to call this our letter L, so that way I can just keep using L for this. So that's going to be what this number right here is representing. And so that way I don't have to keep writing that out every single time. Okay? So if I do that now, I can rewrite this as 3 to the n times this, 3/4 squared, and that has to be less than L. All right? And so I'm going to have 3 to the n over 4 to the n. And then what I can do here is multiply by 9/16. And so in order for me to get this by itself, I can actually then rewrite this by then multiplying L, right? So 3 to the 4th. I need more room here. So 3 to the 4th n is less than L times 16/9. Okay? 16/9. And so I'm actually going to go ahead and now write down what that decimal answer is. And then we'll change up the letters. So 3 to the 4th to the n is less than, and so now our new L, so then 0.5 times 10 to the negative 20 times 16 over 9, this is definitely a calculator question, would be 8.8 repeating times 10 to the negative 21st. And so let's call this now our new letter M, right? So we'll call this right here our actual M, right? Go ahead and add the natural log to both sides, right? So the natural log of 3 over 4n must be less than the natural log of m. And so I can now move down the n with our power of our exponents, our power of our logs. And then we can now say n must be less than the natural log of m over the natural log of 3/4. To do that, we're going to get that n must be greater than. Now, you may ask yourself, well, why do we change the sign? Guys, remember that this right here, the natural log of 3 over 4 is the natural log of 3 minus the natural log of 4. So this is actually a negative number. So we're dividing both sides by negative numbers, so we have to change the sign. And so when you put this in our calculator, we're going to get 160.48. Right, 160.48. So to go back to our question, it says how many terms do we need to get this approximation, right, this approximation of our series to 20 correct decimal places. Well, through this process here, we need 161 terms. So if we were to add up 161 terms, we're going to get this actual error to 20 decimal places. So I hope that makes sense. So I'll chat with you later. So I will see you guys in the next video.